Good morning, good afternoon, good evening, everyone. Thank you for joining us today. We are thrilled to have you here for this exciting session on performance evaluation of V-port ball valves using autonomous valve CFD. Whether you are a valve designer or CFD engineer, today's webinar will provide valuable insights into how the latest CFD technology is transforming valve design and optimization. Let me introduce myself. I'm Praveen. I'll be your host today. I've been working in the field of computational fluid dynamics for over 15 years, helping businesses bridge the gap between technical intricacies and market needs. So I'm delighted to have Akshay here, Akshay Dorle, business manager for autonomous valve CFD at Simulation Hub. Akshay brings over multiple years of experience at CC Tech, where he's kind of balance leading client engagement, technical guidance, and product support for AVC. He works closely with valve manufacturers to ensure they successfully adopt this powerful platform. Akshay holds a master's degree in mechanical engineer from NIT Silchar and has a solid foundation in CFD, making him the perfect expert to share valuable insights on optimizing V-port ball valve using autonomous valve safety. Now I'll hand over to Akshay to get us started. Akshay, the floor is yours.
Thanks a lot, Praveen, for that wonderful introduction. Yeah, so let's start with today's webinar. So this is the agenda for today. We'll be understanding V-port ball valves, but before that, we will get an understanding of flow control, the evolution of flow control, why flow control actually matters in industry. Then what are the valves that can help us in achieving this flow control? And then as the topic suggests today, it's regarding V-port ball valves. It's you can say a modification to the conventional ball valves. So we'll look at ball valves advantages and limitations. Then we'll get to the crux of V-port ball valves. What is the concept? What are the geometries used in industry? Then we'll look at some nice case studies that we have done. And then we'll have a look at the customer success stories, which of the customers who are using our simulation platform AVC, and we'll have a quick Q&A session. So moving along, let's start with the evolution of flow control. So in the early stages of valve design and valve applications, the main purpose of having valves installed in, let's say, water management pipelines or any other industry was to get a good sealing of the process fluid and to control the flow by just either having it completely off or having it completely on. So in this, we have gate valves, which are used in dams. We have plug valves, and even you might have seen in like PVC ball valves, they are still used as basically on-off valves. And the goal for these valves was to have the least pressure drop, pressure losses, while having robust sealing. Now, as the industry evolved, as the interest of industry and the advent of industrial revolution came along, it required a lot of control of these process fluids, as they would not just have flow to be regulated, they also had like temperature and pressure and all sorts of parameters that needed to be controlled. So we needed good throttling control with the conventional valves. So you can say the interest is to have a very good control over the process fluid, depending on where the valve is used. It could be used in pharma industry, it could be used in food, industry, it could be used in paper industry. So a good control over the process fluid is the need of the industry. And earlier they used to be manually operated. So still valves, there are valves that are manually operated, but with industry 4.0 and the digital age, we have to control valves with without any manual intervention. What this does is it gives us a predictable flow control over the process fluid, and uh, it gives us very efficient and stable and safe environments to work in the industry with the correct, you can say, flow control. So moving along, why flow control matters. So as I've said earlier, with the industrial revolution, many industries came into being. We have oil and gas, we have water management, we have power generation. So all of these, we have HVAC industry. So all of these industries need a very good control over the process fluid. And that's where valve design comes in. That's where valve control and valve flow performance comes in. So it's very relevant to the industry. Like I guess just in one plant there might be thousands of valves being operated, and they could range from gate valves to ball valves to all sorts of valves. So it becomes very relevant to the industry. With proper control, you reduce energy losses, you improve the optimization of the entire system, you optimize your systems as a whole, you avoid unnecessary vibrations, unnecessary shocks, noise, and all of these unwanted phenomena through the control. And it also gives you a precise flow over multiple control systems. So moving on to reliability and automation. So with the digital age, we can basically have various actuators. We can operate them through control signals. We can just get real-time feedback. We can make digital twins for the entire setup. So it matters a lot in terms of reliability and automation. So moving along, we have the industry standard control valves. So Global is the best example here. Global is excellent in throttling the fluid. It gives you precise control as the travel is linear. It gives you a very good control over the process fluid. The drawback is due to the complex flow and the flow fluid changing directions many times, it gives rise to a lot of pressure losses. But having said that, it has a very precise control application. Ball valves, on the other hand, they are very compact. They are cost effective. In full opening, they have they are like a straight pipe. So there's very less pressure drop as compared to globe valves. And butterfly valves are also used in control applications. So they are suited where large valves and basically controlling flow through large pipes. So you might have seen in maybe water management industries and oil and gas, butterfly valves are very readily used. Apart from the globe valve and butterfly valve, there are also plug valves, pinch valves, diaphragm valves. So pinch and diaphragm valves use a deformable body to control the valve. And yeah, so these are the flow control valves readily used in the industry. So moving to the topic at hand, it's related to ball valves. So and V-port ball valves. So I'll just list out what are the advantages of ball valves. Why do we care about ball valves so much? So ball valves, again, as I've mentioned, very simple mechanism. It's a quarter ton valve as compared to a globe valve, which is a multi-turn valve. So if it's manually operated, you have to, turn it a lot to get that linear actuation. In case of ball valves, it's a quarter-turn valve. It's easily opened and closed. It has very good sealing. So even at low operating torques, you will get a very good sealing for ball valves. And with the straight, like the bore is very straight. It's the same as the pipe diameter. So there's no chance of pressure loss, maybe some minor losses due to friction. But as compared to globe valve, but ball valve has very less pressure losses. The limitations in ball valves are you can't control it. As you open the valve, as you try to throttle using a ball valve, it might work for a few days, for a few hours, but prolonged exposure to the process fluid and high velocities, it will lead to erosion. And this could be it will damage a valve. It can also lead to some safety issues in the entire system. And it's not ideal for precise control. So to get precise control, not as precise as globe control valve, but very close to it, at the same time having much less pressure drops, much less pressure losses as compared to globe valves, we'll have to make some modifications to this design. So here we introduce the V-port concept. So in this concept, what happens is we, instead of having a full port, so if I'm able to show you like the full port in the image here at the bottom right corner, we can precisely control the valve using the geometry additions of these V notches. So what they do is they take out the limitations of a conventional ball valve. They give you precise control with the compact size, and at full opening, you have much less pressure drops as compared to a globe valve. What it adds to the conventional globe valve is your CV is much more controlled and it's much more predictable. Now, as opposed to a full port ball valve, you can have a better prediction of your CV. You can even get, depending on the notch angle and the notch dimensions. So right now, the images show a standard size of notches that are usually used, but you can even customize these notches. You can have uh, a different design to suit your performance characteristics, such as maybe you want it to be equal percentage, or maybe you want it to be more linear, you want it to be more modified linear. Playing with these notches and the designs can help you achieving the goal whilst reducing the pressure losses. The common configurations are noted here, which is 15, 30, 45, 60, 90. And as the design suggests, you have at 15 degree, it's a small opening and it gives more control, but lesser flow. If you move to the 90 opening, it has more capacity, more CV, but it tends towards the full port configuration, so it has a lesser control. So yeah, conventionally, to size the walls, we use flow loop testing to precisely size the walls, and the output parameter from these tests are CV and CDT. So conventional flow loop testing is conducted to obtain CV in certified laboratories, and they are conducted in accordance to the IEC 605-34-2-3 and ANSI 750201 standards. And the common test facility in India is FCRI, and in the US, it's Utah Water Research Laboratories. And the schematics show the test setup for the flow loop tests. And so where flow loop tests come into picture is in the new product development. So whenever the end user demands for a certain industry, for a certain application, the CV is what he will specify. And for achieving this, you will go to a design engineer, you will give him the parameters, you will say, this is my target CV, can we design this? And with using the expertise, some standards, and the insights from experience, you will model the geometry, you will manufacture a prototype, and then send it and transport it to a flow loop testing facility. So from manufacturing the prototype, it takes time. The flow transporting it to the flow loop facility, again, it's time consuming. And the flow loop tests will give you a CFD report. Now, if the if the flow loop test will give you the CV and CDT parameters. If the CV and CDT don't match your target CV, you have to again repeat this cycle, and it takes from weeks to months to get to a final design iteration of the wall for the particular target CV. Results in weeks, even in months. There might be a waiting time for testing and stuff. So again, it's from weeks to months. So what are the challenges in flow loop testing? It doesn't give you insight. It gives you a CV, it gives you a CDT, but it doesn't give you anything insightful. You can't visualize the flow. You can't see where the cavitation might occur, what are the intricacies of the flow, and how your design is affecting the flow. Second, cost and time. It costs you to model the prototype, actually manufacture it, send it, test it. If parameters have to be switched, if the few design modifications have to be made, again, it leads to added cost, added time. And there's a resource limitation, in the sense small walls can be tested readily, but imagine sending like DN 2000, 3600 walls to testing. So it's almost impossible to test these walls. So there are alternate methods. One is the actual flow loop test. It's very accurate, as it's the real life thing. It consumes a lot of time, it consumes a lot of cost, and the skill required is very less. On the other hand, we have analytical method, in which we use empirical relations and design simplifications to basically get a quick CV. It's very cost efficient, very time efficient, and there is some skill involved in it. But CFD, or the numerical method, is very accurate. It will take generally more time than analytical method, but the accuracy is very close to real life. The time is much less compared to real life testing. The cost is associated to the CFD engineer, to the you can say the equipment, meaning the high performance computing system that you have, and the skill required is very high. You need a CFD engineer who knows the tool and what insights to extract. So challenges in analytical methods, as we have briefly seen, limited to trim design. So again, we cannot get insights of flow from analytical methods. It's quicker than flow loop testing to get a CV, but those insights are missed. Second, complex designs cannot be evaluated because there will be too many design parameters and there's too many empirical relations to get to the CV parameter. And as the design changes, your empirical relations might need some correction factors, some correlation factors, and again, it's a laborious process. Coming to CFD, so CFD is a science. It's an art, but if done scientifically. So it's it's a methodology to predict flow, heat transfer, and complex flow phenomenon. So basically what it does is it solves the Navier-Stokes equations. So Navier-Stokes equations are the governing equations to model flow physics. And it solves these equations using a finite volume method. And finite volume method is basically defining your domain, breaking it down into small volumes, and integrating your parameters and solving it on the entire domain. So CFD is the tool to give you very insightful pictures, insightful understanding from your your designs. It gives you the CV. It gives you various parameters like flow separation, where the flow is accelerating, even insights about cavitation. So we'll see the conventional CFD approach. So in conventional CFD, you need a CAD file. The fluid volume, meaning the surfaces, the wetted surfaces of the domain need to be extracted. It has to be meshed. It has to have the correct boundary conditions. And you need a high performance computer or a HPC system to run these calculations and simulations. And then you get your insights and you get your flow characteristics like CV. What are the challenges in CFD is it needs an expert. It needs the domain expert. It needs the CFD engineer. The process is manual in the sense of cleaning up the CAD, having the right meshing parameters, having the right boundary conditions. It takes time. And in case of bad meshes, it can lead to divergence. Then you have to go back again, tweak the mesh, repeat the process. So it's very laborious, very manual intensive. It needs a good high performance computing machine on premise. You can run CFD simulations on a low configuration machine, but it will take you hours and days to run it. And license cost. So conventional commercial CFD products will have one license per user. It will be limited annually, or again, there's constraints in terms of license as per the user. And if you have a lot of design engineers in your team, you have to wait in queue to run your simulations. Then the other designer can use it, and it's a long wait. This is where autonomous valve CFD comes in. It's a specialized CFD platform, CFD tool for virtual flow loop testing. It refers to ANSI ISA 750201 standards that we saw, which are used in actual flow loop testing. So the parameters are tweaked to follow the same procedure, and the output you get from this application is CV, KV, CDT, sigma, which is the incipient cavitation index. So this is a platform which is powered by 3 powerhouses. So the image that you see here, it's the Valve, which is being viewed in the Autodesk platform services. This is a cloud. It's a web-based application which runs simulations on cloud. So we use AWS for it. Again, it's a powerhouse in cloud computing. And the backend solver for this is OpenFOAM, which is very well known in the industry and even in academia. This it's very versatile, customizable solver. So autonomous valve CFD, the process is straightforward, meaning a design engineer just needs the valve CAD model, 3D CAD model. Any step file, parasolid file can be used. And the user has to just define the flow directions, define the opening conditions. By opening conditions, in rotary valves would mean the angle of opening. In globe valve, it would mean the stem travel. And that's it. Once those things are specified, the autonomous valve CFD platform takes care of running the entire CFD workflow. you have, after the simulation, you have velocity contours, flow lines, surface pressure, minimum pressure locations. The very insightful insights or the insightful parameters that you get from CFD are visualized in AVC. You also get quantitative data in terms of plots and graphs and tables, and everything is consolidated into a CFD report autonomously. So you get all the quantitative data and the qualitative data in a concise, crisp CFD report. The walls that are supported in AVC are as follows. So we support all control and isolation walls, ball walls, we support full port, reduced port, and obviously the V port ball valve. We have a globe valve in linear motion as well. And similar things can be used for isolation configurations as well. In recent times, we have also started supporting axial flow check valves and axial flow control valves. So it's the app also gets updated as we interact with new customers, new designs. So as the topic suggests, we are supporting. So we will have a quick look at the demo precisely for today's discussion. That is the V-port ball walls. Yes. So AVC is a web-based platform, and along with Valve, we also have different products for buildings and HVAC domain. So we'll start with a 3-inch V-port ball valve with 30-degree of V-port, and we'll just quickly run through the demo. So first step is inputting the CAD model. So we support step file, IPT file, SAT file. We just have to upload this file. Again, if you have concerns regarding, okay, it's going on the web, it's completely encrypted. We have banking level of security for this. So it's way more encrypted than your emails that you might send to end users and clients. So we'll have a look at the V-port wall. So it's already added in the drop down. You have to just choose the size, specify the flow regulation. Is it flow regulation? Is it isolation? Specify the roughness, the materials. It's very easy interface to interact with. Just have to click some buttons and that's it. The second step in the simulation is selecting of the moving parts. So here we get to the control part that actually controls the flow. And with the power of APS, we're able to interact with the CAD design, select the necessary parts, and specify the correct rotating parts. We can view it. Then comes the axis of rotation. So again, it's very easy. You just have to select a cylindrical part and it will get the axis of rotation autonomously. It by default populates various angles of openings from 10% to 100%. We can even preview this. So once we click the preview, it opens in the correct way. If it doesn't, we can even reverse the direction. It has the capability to do that as well. The next step comes in the AVC is specifying the flow direction. So we'll just quickly see that. Very easy interface. We just have to select, click. No complex things. Very easy. We just clicked on that button, clicked on the CAD, and it automatically detected everything. So these are the 4 steps. This is done. Once now we'll submit the simulation and that's it. The design engineer can now go work on some other design, some other iteration of the same design, or run a different, completely different valve on the same platform. It's a credit-based system, so 10 openings have consumed 10 credits, 1 credit per opening. And the autonomous workflow takes care of all the CFD simulations on the cloud. So from extracting the fluid volume to post-processing your results, no need of CFD expertise. The app is the CFD expert in your team. So once you have run the simulation, you can post-process various parameters. So one is the flow lines. You can check how the flow is moving through the valve. You can also use these images in your catalogs on your website to showcase your intricate valve design. We also have contour plots. We have surface pressures. So here we can check the zones of very high pressure, very low pressure. So these are the insights that you get from this. And as always, you have contour plots. Again, these will give you the areas of uh, flow acceleration. So I guess it's loading a bit. Give me a second. Okay, seems like it's stuck. We'll move on to the, give me a second. Yeah, just see if it works here. Okay, we'll move on to the next part, which is AVC will empower you to test your new V-port valve designs. So we have taken a few references which manufacture V-port valve design, and we can see the simulations have been done in AVC, and a nice streamline image uh, shows how the flow is flowing through the valve. Validation studies. So we'll take a look at validation study. Now, till now, we have said, okay, AVC is great. It's autonomous. It's web-based. No limitations on number of designs. No limitations on number of licenses. So, what is the credibility of this? So, we have done validation studies, and I would like Praveen to explain to the viewers how and the impact of these validation studies and how it benefits our users.
Thanks, Akshay, for walking through the demonstration and stuff. So going ahead, validation studies, like it's very important for, especially for the autonomous workflow, right? It needs to be very accurate. Yeah. So going ahead, yeah. So what we have done is we have done validation of our CFD results and compared it with the test data from different laboratories for a wide range of valve types and sizes. You can see the CE value and the valve types covered include butterfly valve, all types of butterfly valve, offset, full port, ball valves, globe valve, and segmented ball valves as well. So the accuracy, what we observed is it for almost every cases it falls in plus or minus 5%. There are few outliers that to again it falls in that 10% deviation range. So it's pretty reliable, and the algorithm is fine tuned based on these studies. And on top of it, what we do is when we engage with a customer, we take as a pilot project, take their previously done cases, and then we do validation study to increase the uh, trust factor. So that activity can also be done. So going ahead, so Akshay will be presenting the case studies for VNOS. There are some interesting case studies we have done, the team has done. So for different V nodes, how the flow characteristics vary. So it's very interesting. I'm looking forward to the case study. Yes, actually.
Thanks, Praveen. So, getting back to the topic at hand, it was V notch and V port ball walls, and we'll see what is the impact of this V notch. As we have seen, there are standard angles of this V notch and how they impact the flow characteristic for your walls. So, moving ahead. So, the first study that we have done is uh, the impact of uh, V notch on the flow coefficient. As we have discussed in detail, that full port ball walls, we don't get good control over the process fluid. So we have added the V notch to the design, and in the plot that you're seeing on the screen on the right side, we have simulated the valve using AVC for 10 openings, and we can see in the CV plot itself that as the angle of the notch increases from 15 degree to 90 degree and full port, the CV is increasing. A quick note here, the size of the valve for all of these different V notch designs is 3 inch. So it's a 3 inch ball valve, and we have analyzed the CV performance for each of these notches. So lower the notch, we are getting a kind of a linear flow characteristic. And as we move from 15 degree to 90 degree, we get higher CV, and also the flow characteristic changes. It's moving from linear to say equal percentage, and in full port ball valve, it's it's the characteristic of the full port ball valve. So the insight from CFD that we get here is, as the V notch increases, the maximum velocity in the domain will go on decreasing. So in the contour images here, you can see the jets created by the 30 V ball valve are high in magnitude, and as the V notch is increased to 90 degree, the jets have reduced or in magnitude. So this helps in understanding the vibration behavior, the cavitation behavior in the valve. The next impact that we have studied is the hydrodynamic torque coefficient in the valves. So again, it's for the same 3-inch valve, and we have checked the torque coefficient from 15 degree notch to the full port condition, and we observed a very interesting thing, or an interesting pattern, is that with lower notch angle, you require a lower torque to operate these valves, and that's where the V notch can come into play. Meaning you have to size the actuators accordingly, and the CFD analysis can give you those insights. So these are the insights that we got. For smaller V notches, the flow is more controlled, so it's uh, less torque is required to operate this valve, as there are uh, for the same size, the flow is less because the obstruction is more. As we go on increasing the V port, the CDT is increasing, meaning you need to size the actuators accordingly to fit your application. And this can be done only through CFD, or you can manually test it. But again, before going to modeling the actual valve, you have this insight at hand, and you can provide these insights to your end customers or to your internal team to size the actuators correctly. So Praveen, I would like you to take over from this.
Yes, thanks, Akshay. So here, just to summarize, what we take as an input from the user is the CAD model and the moving parts and the specific opening conditions for which you want to evaluate the CV. And then define the flow direction, whether it is a flow to open or close kind of thing. Next. And what we do or what the software does in the back end is all the CFD processes, cat cleanup, fluid volume extraction, mesh generation, and the CFD simulation, monitoring, setting up the problem, selecting the right turbulence model and numerical methods, and monitoring the convergence, everything. So everything is taken care by the process. The algorithm takes care of it. So user doesn't need to worry about it. And going ahead, what you get out of the software is three things. One is the qualitative results, the flow lines, contours, and other insights, and the quantitative results, which is the CV curves or the CDT and cavity kinetic, the flow performance curves, and the report, auto-generated report combining both the quantitative and qualitative results. So that's it. And how we are able to do this, like what happens behind the scenes, like how it works. So just a little insight about it. So what happens is when you upload the CAD model and the settings, like specific opening conditions. So AVC assigns a dedicated AWS instance, EC2 instance, 36 core machine, and on which the simulation of platform APIs are called for separate jobs like cleanup, meshing, and solve. Once it is done, then it is post-processed and send it back to your browser, like on your machine. So on browser, you can view the results, both the qualitative as well as the CV value or CDT value. So this is, let's say, this is for one opening condition. The same thing happens for all the opening conditions simultaneously, parallelly. So unlike the conventional methods, like conventional software, license constraint and the machine constraint, everything has to go in sequence. Here, because it's a cloud native flow simulation software, so there is no constraint as such. So each opening conditions run parallelly, and then at the end of 1 or 2 hours, you get the complete picture, the complete CV curve out of it. So not just this, let's say you have multiple design, like trim designs you would like to evaluate. So you can upload them, uh, simultaneously, and all the simulations for all openings, run parallelly, and you get the comparison of CV curves. You can simultaneously, like at the end of the, 1 2 hours, you get everything at your hand. So that's very, fast and useful. So on top of it, let's say you have multiple teams working across globe on different products and different product lines, different series. So they can use the software parallelly. There is no constraint, no interdependency on the machines or anything. So everything runs simultaneously without any dependency. So that's what the power of he. So summarizing everything, so it's a little comparison of conventional and the autonomous approach. So in a conventional CFD, what happens is simulation experts dependency becomes a bottleneck. So he does the all the CFD processes manually, and then runs the simulation on limited in-house resources, and then that takes weeks of time, and then you get the results. So the cost is higher. So on the other hand, simulation of CFD, what it does is the process is autonomous. So all the CFD processes are done autonomously, and the cloud platform is used. So it expands depending on the number of openings, number of valve size and mesh. Everything happens on the cloud, so it's pretty fast. So you can get the complete CV curve in hours. So the cost is also very less. So going ahead, so I always used to take this analogy or like metaphor kind of thing. So general, like when you want to plant a small, seed or plant a small plant in your garden, will you use a big, bulldozer kind of thing, or you use a gardening equipment, right? So this comparison is kind of, general conventional CFD softwares is kind of general. You can solve even a pipe to complex, very complex aerospace kind of problem, combustion kind of problem. So it's like every option is open to you. It's very complex and to use. On the other hand, what we have done is we have verticalized the application and made it only for Valve specific. So I can proudly say we are the only first and only software which has been fine-tuned for Valve CFD simulations, that too on cloud. So that's the analogy I use. And moving ahead, so here these are our customers of Valve autonomous Valve CFD. So we have Bray controls, flow management systems, Flow Tight, and Indian customers like Delwall, Magwin. So all sort of customers across the globe using the software. So I have picked Bray success story, and then let's dive deep. So Bray International is a like biggest valve manufacturer in North America. They have offices across the globe, and they have design centers in Bangalore and Chennai, Houston. Uh, Next, so the challenge what they had is the flow loop test used to take 3 to 4 months of testing each valve designs, so that considerably delays the new product launch and things. On the other hand, they already had CFD team in house. They were using generic CFD tools. They were limited by the number of licenses they have, and the CFD experts were overworked. So there was a large backlog of designs in queue, so the design engineer had to wait for a long time. So it takes up to 5 days to get the CV curve from the CFD experts. So this was the situation before we entered. Then the solution what we provided, so how it helped them. So they were able to run parallelly. The design engineers, they themselves started adopting the software and evaluating their design. They started using the AVC software and uh, completed, get the evaluate the CV curve out of themselves. So dependency on the CFD experts was removed. So CFD experts, they were able to focus on much more complex problems in their traditional software, like noise, erosion, and those kind of problems. And while the normal, the simpler CV, CDT things can was handled, started like the design teams themselves started handling those. So it's a 10x growth from 3 users to 30 users now, and the total number of valves being tested, the design iterations got more and in an accelerated manner. So the experimental cost and comparing to the experimental cost and the normal conventional cost, so the cost benefit was multifold. And then yeah, it also adds to, it saves a lot of physical testings, right? Like only the final test can be submitted and tested in the physical flow loop. So it saves, it help in achieving the ESG goals as well. So yeah, next. So we conduct a lot of workshops, and we interact with the client to understand their pain points and address them and add the missing features in the app, so that so Bray has been kind of sixth or seventh year they are continuously entering into the subscription of AVC. So they are a happy customer. Then next. So this is a kind testimonial from Brindesh. He's the EVP, CMO, and CTO of Bray International. Yeah. So this is just we just wanted to pick one customer study and things. So what's next? So after this, you have two things. You can do two things. One is you straight away start your trial subscription plans. We have 15 days trial and 20 simulations you can do. So depending on the number of openings, you can design as many valves in this trial account. And then on the other hand, you have some more questions or queries to be resolved. You want to involve your design team for and interact with our product experts. You can schedule a call with our expert. You can visit our website simulationup.com, and then you can press request demo, and we can schedule a call, and as per your convenience and time zone, we can interact and take it forward. So we are towards the end of this session, and we want to announce one more thing. The normal trial, there are limited credits and limited time period. So for this webinar attendees who schedule the demo call with us, we are extending the trial period to 1 month and with more simulation credits. So on top of it, we also conduct the validation study as a pilot thing. It's a free of cost activity. So for webinar attendees, you can give that reference, and you can schedule a call, and we'll be happy to help you and interact and take it forward. Thanks again for your time, and we started a bit late. So apologies for that. But thanks for patiently waiting. So now you can post your questions. Already we have received a few questions. So I'll be like happy to answer those. So we got one question from Mr. Gajendran. He says, is there an option to identify the choking condition at Venor Contracta using uh, AVC? Yes. Gajendran, actually, what we provide is there are two parts to it. One is the incipient cavitation index. We provide the app provides incipient cavitation index, which can be used to predict the starting point of cavitation. And the other hand, if you talk about choking conditions, uh, there is a parameter called liquid recovery factor. So it is FL. So that needs some additional steps. So we are bringing them to the app. But meanwhile, our support team supports get involved and can extract FL for you. So that will help you to check the choked flow rate, maximum flow rate, and stuff like that. So another question about accuracy, I guess that's already covered one of the slides. Like, yes, we do compare our results. We have compared our results with the test data. So we observed like plus or minus 5% deviation in most of the cases. And to on top of that, on an individual basis, like whenever we connect with the company, like manufacturers, so if they have their old data, test data, then we also do specific comparison study, the validation study to that. Yes. So there is one more question from Vinayak. Which design is better, V-port or V-port on seat? Akshay, any insights on this?
So that's a very interesting question, Vinayak. We have observed in the industry that there is a characterized disc that is used in which has that V notch as opposed to actually having the V port on the ball. I'm at the moment not completely sure which would be the better design. Uh, just going by the case studies and the initial findings that we uh, got from this case study is the V-port design on the ball will give you a better regulated control and a better predictable CV. In terms of characterized disk, as it's a combination of the full port ball wall with a different disk, the flow paths are kind of disconnected and it might give some unpredictable behavior. But having said that, you can definitely test both of those designs on AVC. So you can actually run a comparison study on AVC for this particular query, and these insights can be obtained for your design.
Yes. Thanks, Akshay. So, and there is another question from Joan. Like, oh, okay. He's asking, will you be sharing the recording of the webinar? Yes, the webinar recording will be uploaded on our website, and you'll get an email. You can check over there on our website, and you'll get it maybe in a couple of days. So we'll upload them, and it should be there for your access. So we are already, spilled out of our actual time. So there are a few more questions, but what I prefer is, I guess, we'll answer them on personal basis, and we'll email them with the. You can also, in later stages, if you have any queries, please feel free to write to me. You can find the email IDs on our website, or you can directly schedule a call with our product team. So they'll be happy to connect and help you out. Thanks everyone for their time, and thanks Akshay for the wonderful presentation. And yeah, looking forward to the next topic and next webinar. Thanks.
Thank you, Praveen. Thanks, everyone. Yeah, have a nice day. That's it.